Okay, so at the end of the 17th century, we were talking about the atom in the last video and kind of how it came to be what we understand it to be. So Democritus suggested that you could take something and break it down keep breaking it down and breaking it down and breaking it down till you got to the point where the particle you had left couldn't be broken down anymore. And he called that an atom. Unfortunately, what we call an atom today isn't actually what he would have intended. Atom means indivisible one, but what we call an atom today we can divide. So in a way we used what we termed an atom, we termed it too quickly. When we thought we found what was indivisible, we assumed back then that it couldn't go any further, but then as we continued in our growth of technology and our science abilities, we are now able to split the atom. So it's an atom that's not really an atom. Anyway, so Robert Boyle so this was 400 BC. Robert Boyle began to use the term in the 17th century when he came up with Boyle's law, where he noticed that if you had a gas and the more pressure you put on a volume of gas, the more the volume decreased. As pressure increased, volume decreased, and vice versa. So he imagined these little atoms being some distance apart and putting pressure on them, put them together, and decrease the volume. And then we were at Lavoisier and Proust. Now, Lavoisier and Proust were looking at chemical reactions and looking at how it was always the same ratio of reactants that would react. Like, so if they were doing some kind of a chemical reaction, then it would be like, even if they were looking at masses, maybe 20 grams of something and 10 grams of something else that would react to give you the products. So they noticed that they always reacted in the same proportions. And so what they said was, so it must be that there are atoms here. So like 2 atoms of one substance reacts with one of another in that ratio all the time. So again, the word atom comes up. And then in 1808, John Dalton created what he brilliantly called the modern atomic theory. And actually, anything from the 1800s is often referred to as modern physics, because for them that was modern, that was the times, right? For us now, it's not modern, but they thought it was back then. So John Dalton, in his modern atomic theory, came up with a model of the atom that I think you may have learned as the billiard ball model. And he said when you have a pure element is made up of identical tiny particles. So all of the particles in an element are identical tiny particles, which of course he called atoms. So identical atoms. Whereas different elements, so a pure element, this might be copper, it might be aluminum. So copper would have all the same elements inside of it, and they would all be tiny little. But different elements would have different tiny particles. So that the tiny elements that copper is made up, different elements have different atoms. And up here, I guess I should say atoms. So copper would break down into tiny little atoms. Aluminum would break down to tiny little atoms. All of the copper atoms would be the same. All of the aluminum atoms would be the same, but they would not be the same as each other. So different elements would have different atoms. And then the third one was that combined substances, what we would call compounds now, are made up of a combination of different atoms. Combination of different atoms. So the pure elements were all the same, but the compounds would have like copper in there and maybe sodium in there. Okay. And they were always in the same set ratio. Always in same set ratio. Okay, like whole numbers. So like water, H2O. There were always two hydrogens that went with one oxygen. Okay, so that was Dalton. So again, what we're doing right now is we're tracing like where the notion of atom or how it came to be. The next time it appears is in Avogadro's number. Avogadro's number, which hopefully you remember from chemistry, is the number of molecules in a mole. 6.02 times 10 to the 23rd molecules per mole, or atoms per mole. Okay? So again, this smallest entity is coming into play. And so through all of this, people were like, but what does this atom look like? Like, what does this small, indivisible one look like? And so J.J. Thompson is probably one of the first models that's best known, 1897. And depending on who you learned it from, maybe the plum pudding model, or the Raisin Bun Model. It's called both, depending on language and area. Raisin Bun Model. I'd rather like the chocolate chip muffin model, maybe. Okay, so this model, it's simply saying that inside this atom, there's a uniform distribution of positive charge. And the negative charges are like embedded in them. So for the raisin bun, the bun is the positive charge, and the electrons, the negative charge, are the raisins. Plum pudding, the same idea. Chocolate chip muffin, same idea. So whatever the little entities are in here, chocolate chips or raisins, they're the negative charge, and the dough is the positive charge. Okay, J.J. Thompson's model was proven wrong when the electron was isolated. And the electron was isolated by J.J. Thompson. So I guess the good news is he proved himself wrong. It's probably better than someone else proving him wrong. So after J.J. Thompson found the electron, then another... so all through this, people are working on what does this atom look like. So the next model that comes up is by a guy who's working after J.J. Thompson isolated the electron. He isolated the electron, I want to say, in 1909. And so the next model is Ernest Rutherford, 1911. So not very long after the electron was isolated. And his model, I think it's technically called the nuclear model. You probably know it as the solar system model. And Rutherford did what is now a very famous experiment. It's called the alpha particle scattering experiment. Now, he used alpha particles, even though he didn't really know what they were back then, but we know what they are now. What he knew alpha particles were particles that were given off by a substance that was radioactive. They're the first radioactive particle to be discovered, and so they were named after the first letter in the Greek alphabet. The symbol for an alpha is the Greek letter A, alpha. Now we know that an alpha particle is actually the nucleus of a helium atom. It's two protons and two neutrons together. So it's not like two protons and two neutrons given off as four separate entities. It is a single entity that has two protons and two neutrons inside of it, which they named an alpha particle.